Welcome back. Want to continue with our lessons on writing zero knowledge proofs and also deploying them after we've written. We had begun looking at the concept of zero knowledge proofs last week. So we just continue. We are writing in NOIR or NOIR. So, we did installation. Felix, did you install? Have you installed it? NOIR. Okay, I can't hear you.
Not quite yet.
Or you've not installed, huh?
Yeah.
Yeah, so you'll just follow, then later on you may want to install. And there's quite a number of things you need to install before you write these zero knowledge proofs using NOIR. One of them, of course, is Rust, which you already installed. Rust, I know this one you have it.
Yeah.
So you also need to install NOIR itself. You need to install Nago. There are several things you need to install other than just the three I've mentioned. The others you need to install, but I'll mention them as we progress. Now, so today's objective is just to write zero knowledge proofs, circuits, and then see how to deploy them. I'll just do an example. The example I'll be doing is where you are verifying that your age is within a certain range without necessarily revealing what your age is. So let me say you are the prover and you want to prove that your age is between, let me say, 18 and 52, without necessarily letting anybody know what your age, the exact age is. That's what we'll be doing. We'll be writing a circuit that will be doing this, where the prover will be proving to the verifier that his or her age is within a certain range without necessarily telling the verifier what the age is. So this is zero knowledge proof because at the end of this process, the verifier should not know what your exact age is, but he must know that you have proved that your age is within the range specified. Now, so that is the example we're looking at today. Of course, we looked at another example last week. So we're just progressing with these examples.
Hello, members. How are you? Hello.
Yeah, good.
Thank you, Doc.
Okay, sorry for that. Now, so what we will want to do in today's lesson one, want to understand how to construct zero knowledge proofs using NOIR. And two, we'll learn how to generate. After writing the circuit, we need to generate the proofs, verify the proofs, and then deploy those contracts, deploy the contract in a real world scenario. So, of course, we can deploy it on a real network, but today we'll not be doing it on real network. We'll just be doing it on our laptop, or we can also do it using Remix and do it on, no, is it called Remix or what is it called? Yeah, I think it's Yes, it's called that. So we can also deploy it using that to some real network. So that is what we'll be doing. But first of all, we will begin by writing the zero knowledge proofs. Now, but we did quite a number of good work. I know that Kenneth was with us last time, even Nelly. So they have already installed. But Felix, you had not installed. And so what you need to install is what is here. You said you've already installed Rust. So you'll also need to install NOIR, install Nago. And these ones will be used for writing and then compiling, because the commands we'll be using to generate our proofs and the verification will be Nago. We'll be using Nago commands. So you need this to do that, to do the proofs and verification and generation. And we also require Baritenberg. I don't know how that is, how it's read, but this will then be assisting us in proving and verifying the proofs. So that is what it will be doing. So those are the, I think there are 4 or 5. One, Rust, then NOIR and Nago, and then we have this. Those are the only things that if you've not installed, you need to install so that you can do the proofs like the way we'll be doing. But for us who've already installed, so we just go straight to writing circuits, generating the proofs, verifying the proofs, and then we go to how then do we deploy them. And I've said we can deploy them on real network or just on hardnet. Is it called hardnet? Just we can deploy. For me, I'll do it. I'll give you the process for either deploying it on the real network, and also just doing it on your laptop to ensure that you've verified, then you've deployed. So that's what we'll be doing today. So, but before that, we begin by writing a circuit. So today I've said the circuit I'll be writing will be just to prove that the prover wants to prove to the verifier that his edge is between some specified interval. Let's say the verifier wants to know whether your edge is between 18 and 52. And so that is what you'll be doing. You'll be proving to this verifier that your edge indeed is between this range, without necessarily letting the verifier know what your exact edge is. And so that is what we then zero knowledge proof, that is how it comes in. You need the verifier not to know some details about you. It could be a password, it could be something else you don't want the verifier to know, but you want to tell the verifier you know the password, but you don't want the verifier to know what it is. So today we are not looking at the password. We shall look at the password maybe in the next lesson. Today we're just looking at, can you verify that your edge is between given range without necessarily revealing what your edge is. Now, so for us to do that, that is the circuit we'll be writing. And of course, just as we did last time, for those who already have installed this, you go to WSL, go to your WSL and just write. We said that where you're storing, for instance, if you're storing your documents, your programs in a folder, directory, in a directory called Rust programs. That is where you are storing your programs. You cd Rust programs. And then after cd Rust programs, so you then want our program to be called edge verification. You can say NAGO new, then the title of your project, edge verification. Then let me just open my WSL so that we move step by step. Okay, so my WSL is there. Just as we were doing last time, we just follow the same steps, and I've already said. That is my terminal. And my programs are stored under Rust programs. So I just say cd Rust programs. Okay. And I want to create a new program. I want to create a new project. So I say NAGO. You know, when we are using Rust, we would say cargo new. But this one is NOIR, therefore we say NAGO new. Then the name of the program, we want to edge verification. Edge verification. So this is what we want. So I'll just enter. Oh, I've not used this thing for some time. It wants me to install again. I don't know why. If you take some time without using it, it requires you to install it again, and it takes some time. It takes some time to install. NAGO looks like NAGO is not installed again. I really want to go through the process. Last time it did the same thing. Installing it will take some time. I think I can just go through the steps and I'll leave it to install. If it installs, we installed NAGO last time using NOIR. You know, there are two ways of installing. There are two ways of installing NAGO. So you can install it using cargo, the way we did it earlier, and then the way we did it later on, we used NOIR. So let me just ask it to install. And just give the command to install. This is the command to install NAGO. So it appears it's again, since I've not used it, I don't know whether it uninstalls. So it's installing. I don't know how long it will take. Right, so okay. So after that, you just run NOIR. After that, you just run NOIR. I think it's just very fast. NOIR is not found. That's what is supposed. Let me just again repeat the process and repeat that step. Then NOIR. Again, NOIR not found. Okay, I'll install it again. I'll install it later. Let's just go through the process of, we had already gone through this process last week and the other week of writing zero knowledge proofs. Why is it not? Just, let me just again open. I don't know why it's not. Okay, maybe I'll skip that step. I'll skip that step so that we move to another step. Which other step? Just a minute. Just give me some. Again, share it. I see whether it will now work again. Just a minute. Okay, let me again try, see whether it will accept. If it doesn't accept, and then we progress without, by just looking at the steps, because we had already looked at the same thing. So this, we CD Rust programs. Rust programs, and just be sure I've written the correct thing. Okay. Then now go new. Okay, sorry for that network problem. Now, so after CD Rust programs, you say now go new. Then the title of the topic, the topic of your program. Then after that, after pressing enter, you would then CD that topic now, CD edge verification. So after CD edge verification, you would now want to open your editor, which for me, I use Visual Code. So I would just write code, then space, and then a dot, and then enter. That opens this program for me to write. It opens for me a program titled Edge Verification. Now, so this program that is opened, it opens the Visual Code directly by itself. So this code that is opened has the main .nr. It also has cargo-tomil. It has the tomil. But what we're interested in is this, the main. So the main has some default program, and this is what we shall now replace by our program. We shall replace this with our program. So we delete this, what we get there as the code, and replace it with the code we want to write. Now, so edge verification, for you to verify the edge, the main function would be this. This is the main function. So let the minimum edge, because we want this person to verify that he is edged between 18 and 60. We want this person to verify that is edged between 18 and 60. So if that is the case, then we will let the minimum edge be that 18, and then the maximum edge, we let it to be 60. Then we assert that the edge minimum, then we also assert the maximum edge. So this is the whole code. This is the whole code. This code, if you put edge between 18 and 60, inclusive, 18 included, and that is why you can see it's equal or less than or equal, greater than or equal, and then we have less than or equal. So the minimum edge, the edge will be less than or equal to the minimum, can also be less than or equal to the maximum, but then it can also be within the range, within the given range. So if this person gives us an edge between this range, this code will accept. But if it gives us an edge outside this code, outside this range, for instance, give us 17. If you give us 17, it will fail. If you give us 61, it will also fail. But if you give us anything within that range, it will accept. So this is the code that would then be telling us, or the prover will be using to prove that he's or she's within that given age. Now, but this is not the only thing, because you need to test. You need to test. So you add some tests, and the test is what this guy will be using now to test that is within this range. So after writing this main, you also write the test. Just as we did last time, the test begins with the hash, then test. Then we are testing the main function. We are testing the main function. So the test, we are testing if the edge is valid. If the edge is valid. So the one I'm testing this time, I'm testing that 5. And so if I test that 5, if I run NAGO test, you see, after running the test, that is when you write. You can use the command NAGO test. We are doing this in the visual code. We are doing this in the visual code. So when you say NAGO test and you had put that 5, it will accept. So it will mean that the test passes. The test passes. But if you change that 5 to, let me say 16, it will not pass. The test will not pass. It will fail, because we are testing that this person is between 18 and 60. So the edge that it will pass, the test will pass, should be the edge within this range. Anything outside this range, the test fails. So we saw several commands that we can use. We have used the command NAGO test. NAGO test, you can only use it if you've included the test. Remember, without including the test, the above code would still run, will still compile. At that time, you'll be using Nago compile. Nago compile. So when you use Nago compile, without the test, it compiles. But if you want to test, you are using Nago test, you must add the test first of all. You must add the test. Otherwise, if you don't add the test, the command Nago test would not work. That command will not work. So it only works if there is a test. Now, so once you've tested, you've included the test, now for you to proceed and write zero knowledge proof, to generate the proof and verify the proof. Before that, you need to write a prover toml. So you just, this is a new file you're opening. This is a new file. I don't know whether this thing will accept to work this time. I don't know why it's not even working. Let me see whether it will, if it accepts so that we proceed. Okay, so what I can do, let me see what I can open one that works. I don't know whether it will accept to open. Okay, so it's okay, it's okay. It does, I don't know whether it accepts to open. Let me again share it. Let me again share it. So that I can open one that already works, so that one that I already formed, and so that we can edit it. We can edit it. So I think that way we can proceed. That if it accepts to open one program that I already have, so that we can use that instead of doing it theoretically. So just a minute, I want to share. Okay, good. So now I want, let me again, I've shared, I think you can see that. This is my WSL, or the one that refused to create a new program. I don't know why it refused. So let me again cd my Rust programs. Rust programs. That is why I store my programs. I want to see which programs I have, so I write ls. I want to see which programs I have so that I can see which one I can do away with. I can see I have several here. Let me do away with this, our NOIR project. This is the one we created when we began our lesson on Rust on NOIR. So to open that, we say we cd, I cd it, so it's there. Now I say code, then space, then a dot, then enter. It then opens the Visual Code for me, the Visual Studio is open. This on my side, I have it. So what I do now, I stop sharing what I'm sharing, then I just share now the Visual Studio so that we can edit. Okay. Now, so you can see what I'm sharing. What I'm sharing is called our NOIR project. That is what we just opened. You can see on my left where I'm pointing is my NOIR project. Now, so it comes with the Nago Tomil, as I had said, and then it has some main. This is SRC, and then there is main. Then we have this code, and this is the one we want to do away with. That's the way we want to do it, and want to replace it by our code for edge verification. I'd already shared that code. So in fact, what I want is, I want to see whether I can get it. I just want to copy it and paste it to save on time. Let me find where it is. Okay, now I have it. I don't know whether you are seeing what I'm sharing. Before I just, I could be assuming that you are seeing it when you are not seeing it. Are you seeing my Visual Studio?
Yes, we are.
Okay, let me just exit. Okay, so now I'm replacing. I've just replaced the code with the one for verifying the age. It said we want this person to just prove that he is between 18 and 60. So we said we can do Nago compile, Nago compile where it is. Can do Nago compile. Let's see whether it will compile. Okay, so it compiled. Then after compiling, you can see that there's something on the left, something new, target, which was not there, as a result of that compiling. So after compiling, it was successful. So we have target. And inside target, you can see we have our NOIR project.json, which has been formed. So this one has a hash, and the hash is just a hash of the witness, So the witness, we are saying that it should be between the age that, I think it's that age limit, I don't know whether it's a hash of the entire, all the age 18 and some, and was it 60? But now the thing is, our code was able to compile. And so after compiling, you see, we only had main and Nago toml, but this time you can see we have something else. So the other command we said is Nago test, but if I do it now, it will not work because we have no test. It ran, but there were 0 tests to be performed. And so 0 tests were passed. So it does not fail, but it runs. So, okay, it runs, but there was no test. So we have to include our test here. We want to test the edges between that range. So that is what I want to just add there, so that we have some tests to to perform. Otherwise, as it is, it will run. But since there are no tests, the result will be like there are 0 tests performed. So for us to write the test, we begin by test, now hash, and then test. We are testing the main function. So we're just saying the main function is talking about age between 18 and 30. So you're giving it 35 is age between 18 and 60. We're giving it 35 and see whether it will accept. So let's do NAGO test this time. NAGO test. So this time there was some test to be performed. Only one test was performed. You can see, and that test was passed. That test was passed. So the age that was tested is valid, is between the range given to us. So it's valid. So you want to confirm that you're between that range. You see the verifier will not see what that 5 is. It's the prover who is doing this. It's the prover who is doing this. So the verifier asks you your age, and from your end you insert that 5. So this that 5 is not seen by the verifier. Is not seen by the verifier. So, but the verifier from where he is able to see that the age you inserted was within the range specified. So let's try 17. So you put 17 and see whether it will pass. So the verifier from his end is able to see that the age you placed was not in the given range. Was not in the given range, so it did not pass. Let's try 18 itself. Let's try 18 itself and see whether it will pass. That one passes. That one passes. So you put. That is why at the assertion part, it to take care of the minimum. So the minimum age we are looking at should be 18, and the maximum should be 60. Inclusive, 60 inclusive, 18 inclusive. Now, for us to proceed and do, you see, you want to write a contract, you want to do a contract and then deploy. What you'll be deploying will be the contract. So then we require that verification. We require to generate the proof, and then after generate the proof, we do verification of that proof, and from there we get our contract from there. So we'll be seeing how we then arrive at the contract that will then be deploying. Now, so the next command we want to do is NAGO execute. So if I do it now, it will not work. What I want to do, first of all, before I do it, I need to add a prover. I need to add a prover toml. So to add the prover toml, you just come here. Let me just again, where is it? You just click here where I've just clicked on the left, and then you can just right click and say new file. And that file we want to call it prover.toml. Now, so this prover, you just put there the age that is in the test. The age that is in the test. Let's go back to our test and see what our age is. The test in the age here. Which one are we? Oh, yeah, testing 18. You're testing 18. So the prover toml must have the 18. But look at this. We have that 5. If we run, it will not work. Let's see whether it works. NAGO execute. NAGO execute. Oh, where is this? Just a minute. Yeah, it accepts just because for this one it's different. For other cases it will not accept, but for this one it accepts because of our test. Our test is testing anything between that range. So since it's a range, I think that is why it passes. But in most cases, I usually put the same thing. That is where there's no range. Where there's no range, but where there's a range, I think anything you put there in the proof atomic, it will just accept, so long as it's in the range. Let's try on something that is outside the range and see whether it accepts. Okay, this one is not accepted because it's outside the range. Failed constraint. So it's not within the given limit. It's not within the given limit. Okay, so again, now go execute. Now, so far we've done that. Let's look at what has been generated. Everything now is being generated inside the target. Inside the target, you can see everything is being generated there. Earlier on, we had generated our NOIR project.gz, .json. We had generated this one earlier, but now we've generated something, our NOIR project.gz. Now, so it's now that point that I want to generate the proof. Want to generate the proof, the zero knowledge proof, and then verify it, and so on. Before that, let's again come back. Let's just again look what is written down here. When we did NAGO execute, what is written here, it says the circuit witness successfully solved. The circuit witness has been successfully solved, and the witness has been saved. Well, this is where the witness is saved, and it's telling us the exact place where the witness is saved. The witness is saved inside our NOIR project.gz. What is our witness? Our witness, in our case, it's 18. In our case, it's 18. And look what, when you click it, nothing opens. It says the file is not displayed in the text editor because it's either binary or users unsupported. So you cannot see it, but there's a way. If you want to see it, there's a way you can see it. But remember, you are doing it from your end. The verifier is not able to see this witness from your end. You know what it is. Of course, it's you inputting, so you have no problem with what the witness is, because it's you inputting. But now it's done in a way that the other end, the verifier is not able to see it. We say this is private. We also have the public, and we talked about that in our last lessons. When the witness is public, it means the verifier can see it. And we wrote that last time by just including the word pub before the field. The word pub before field. Now, how do we generate a zero knowledge proof? And we said last time that there is no direct proof. There's no direct way to generate the proof by saying NAGO. You see, we've said NAGO execute, we've said NAGO compile, we've said NAGO test, but there's no proof as per now, although NOIR is still undergoing various advancements that are still improving on it, even the NAGO itself. So maybe in the future we would have NAGO proof, but as per now, it's not there. So then that is why we were installing Baran Tech. Is it Baran? That word is hard, but of course you know what it is. That's why we're installing it, so that we are able now to do NAGO proof and the NAGO verification and so on. So the command I'll be using is this. The command I'll be using, first of all, I'll create a directory called target proof directory. And this is where the proof will go. Then I use BB proof. And then there's this scheme, ultra honk, and then there's Oracle hash. For example, Oracle hash, you're using it if you want to generate a contract that will then be deployed on Ethereum. It's compatible when you use. It's normally done by Oracle hash kekak. Is it kekak or what? This is specifically if you want to do it on Ethereum. But if you want to do it on Air, then you'll be using scheme ultra honk. Now, so the only thing I want to change here is the title of our project. And let me just copy it from here, the title of a project. You can just say rename. Instead of renaming, I just want to copy it and then come and change it. This is the only thing I want to change because I had created for edge verification, but it refused to work. Okay, so now this is the command, and this command, what it's doing is creating this directory and then called proof directory. And then inside that, it will put the proof. So let me just copy it. Just copy it and paste it at our terminal. It's successful, and you can see that we have the proof directory. You have the proof directory here. And inside this proof directory, you can see there is a proof, but you cannot see it, but you can cut. You remember last time we did cut and we were able to see it. Of course, we will see it later. Now, so the proof directory has the proof. But the proof directory is also inside the target. Is inside the target. That is why you see, let me again open the command just at the bottom here. At the bottom here, you can see we have target. Inside the target, we have our NOIR project.json. Although that one was already formed, it was already there. Then again, inside our target, we have our NOIR project.gz. Then again, inside our target, we have proof directory. So that is what the command we used. That's the command we used. So the command we used was saying that inside the target, we should have the proof directory. And then inside this proof, we would then have, inside the proof directory, we have the proof. But inside the target, we also have other files. We have the NOIR, our NOIR project.gz, and then our NOIR project.json. Now, so we have the proof. We have the proof. The next thing is we want to verify that, okay, that is not the only, that is, if you remember, I talked about the scheme ultra honk. Then I also talked about the Oracle hash kekak. You can exclude any of them. For me, I put all of them because you may want to generate a contract for something else, or a contract for Ethereum, or to do on Ethereum. So that's why I put all of them, but you could exclude any of them. You could exclude any of them, and the remaining one will still just work. Don't need. If you look what we used last time, this Oracle hash kekak was not there. We used the same command last week. It was not there. So today I've included it, and I've explained why I've included it. Now, the next thing after generation of the proof is to generate verification key. Then you use that verification key to verify. So there are two ways. There are two ways of generating verification key, and then just share my slide so that you see the two ways. And again, the two ways are as a result of what I've just explained. Do you want to deploy it on Ethereum, or do you want to deploy it elsewhere? So there are those two ways. So at this point, when you're generating the verification key, you have to be very specific which one you want. But for generation of the proof, you can combine the two. There's no problem. You're just creating a proof. You can combine these two. But now when it comes to generating the verification key, you have to be specific. You're either going this direction or you're going this direction. So you have to be specific which direction you're going. So the word that I was referring to, Barettenbeck or something, this is the one that assisted to verify and to prove, generate the proof. So that's what I'm using. That is the one that comes with this BB. BB is the one that comes with this command. When you install it, you then have the command. Okay, so the verification key, you have two ways. We have this. This one is using the scheme Ultra Honk. Now, it's the same thing. The only difference is here. And then we have this. This is the other way. And so that means you want to use the Oracle hash. So those are the two ways of generating verification key. Last time we used the first one. We used part A, we generated verification key using the first approach. But today I want us to use this approach so that when you go to, is it called Remix, you can deploy on Ethereum. So I want to use that second way of generating verification key. And so now you understand that there are those two ways of generating verification key. Again, let me just share now the visual code so that we proceed. Okay, here we are. So let me again edit my code here. So this is not the code. This is a command I'm going to use. BP write verification key, write VK, and then the target. Now, so we want this, you see, what is in the target.json? This is what we created when we said compile. So this is where we just saying it, so it's inside the target, but now the only thing I need to change is this title. So let me again copy my title here. The title of our project is our NOIR project. Let me come and just replace it. Okay. So we want to, inside this target, we want to have our VK, our verification key. Okay, it's successful. Successful. When it's successful, you can always see is it blue or green? This. Whenever you see red, it means it's not successful, like we saw earlier on when we did when we did test edge not within the range. We saw we were coming up with something red, so it means it's not successful. But in our case here, it's successful. So you can see inside our target. Inside our target, you can see our VK, the verification key, but you cannot open it because it's either binary or uses unsupported text encoding. So you cannot, you're not able to see it. Now, so it says something here. It says the VK is saved to target /VK. So it's our verification key is saved inside here. And then the circuit is now of this size, 2768. And then we used what? Oracle hash kekak. That's what we used. Now, so the next thing after you have, you see what the procedure was. What was the procedure? We generated verification, our proof. Then after generating the proof, we generate verification key. So we have the verification key. Now with the verification key, you can now verify the proof. You can now verify the proof. And again, to verify the proof, it depends on which command you used to generate the verification key. So we have had two commands for generating verification key. So did you generate using the scheme ultra honk, or did you generate using the kekak? So depending on the way what you used, you would again verify the proof. And that's what I just want to share again, that slide, so that for purposes of completeness, so that the notes are just complete. To verify, okay, there's some, you look at the notes, there's some, I've explained something about generation of a verification key, and I've said there are two ways, and so what determines which way you take, and I've given the differences between those two ways, and I've said when do we use which way. So if you're testing for development, you would use the ultra honk, or if you want to something that is compatible with Ethereum, then you are using Oracle hash, and I'd already explained that earlier on. verification key, you would that the scheme ultra here. So it means again at this is what you have, the scheme ultra home. And then target, that is why we have our VK. Then we output. So that is now the output, and then we store it here. And then we have the target, proof directory, and then the proof. Because this is what we want to prove. Now that is if you had done the verification key using this command. But you may have wanted to use the one that is compatible with Ethereum. And so if that is the case, and then the command you will be using just the same command, only a slight difference is just where there was a scheme to replace by Oracle. But the rest remains the same thing. So that is what we want to do. But of course, before that, I've also explained what these terms use, or what they mean, what the Oracle hash kekak does, and what this one does. The verification key file is saved in this target. That is what it means. And then the proof file generated by this. So this was this one we did it earlier. We had done it earlier. We had done when we generate the proof, we began by creating a directory called proof directory, and inside that we stored the proof. It's this proof that we want just to verify. So I've also highlighted some common mistakes, which I've already mentioned. Common mistakes is where you may be mixing, maybe mixing the two parts. For instance, you generated using the scheme Hong, and then you want maybe to verify using Kekak. It will not work. So you stick on one. If you are using Oracle hash, you stick on that. You see, for instance, you generate the verification key. If you generate the verification key using Ultra Hong, scheme Ultra Hong, you stick to that because after generation of the key, you have to verify the proof. So that means you have to use the same approach, but you don't mix. So that is where that is the only mistake that is somebody is likely to make. Otherwise, when you stick on one, it becomes very easy. Now, so we want to generate, want to verify the proof. So I had said for us, we had used Oracle hash kekak. So that is what we will stick to, and then verify the proof. So let me just again share, and then we verify the proof. So it's here. I paste the command bp verify Oracle something and so on, then verify. So it says proof verified successfully. Proof verified success. We are now done. We verified the proof. Now the thing that now what we want to go and deploy is what we call the solidity verifier. The solidity verifier, now that is the next thing. Again, it will depend on the method we used. It will depend on the method we used to create the verification key and then verifying the proof. So it will depend on which method did we use. So the method you took is the same method you would still take to create solidity verifier. And solidity verifier is what will give us the contract that we will then be wanting to deploy. Now, so that is the next thing. That's the next thing, solidity verifier. And again, just as before, I say there are two ways to get the solidity verifier. The first way is to use the scheme ultra honk. And last time in our last lesson, this is what we used. Because in our last lesson, we were using the scheme ultra honk, but today we are using the hash kekak. Now, this is how you then generate a solidity verifier using the ultra honk. So you can see you make a directory. Inside the directory target, you say bp write solidity verifier, and you're using scheme ultra honk. And then this is the same thing we had earlier. And then inside this target, you want a file called solidity verifier. You want a file called solidity verifier. But now, if you're using this method, there are two ways. No, there are two steps. You have to create this solidity verifier. So it will be created this way, to be created solidity underscore verifier. But what we want to go and deploy is supposed to be, just a minute, sorry, this pen. Okay, supposed to be solidity verifier dot sol. So what that means, you have to, if you're using this method as we did last time, you create this solidity verifier. Then after that, you move it to solidity verifier dot sol. You move it to that, just as we did in our last lesson. So you create the solidity verifier. This generates solidity verifier as a file, and it will be named solidity verifier. It will be inside the .target directory. But now to make it usable, you need it's supposed to be .sol. So what you then do, you write on the same, that is on the same terminal, you can now write, you copy this link, which is, this command, which is move some space .target solidity verifier, because this is solidity verifier is inside the target. So we want to move this to target solidity verifier .sol. It's only that my slide ended before. It's supposed to be .sol. Solidity verifier .sol. So you're just moving this to this. So maybe at your own time, you can try to see whether you can rename it, whether you see we also have rename. You may just even rename it because you said the same thing. Just moving this to this. So the only thing I'm changing is that I'm just adding at the end here .sol. So maybe you can just even rename it because that is what you want. That is what you can use. You cannot use solidity verifier, but what you use is solidity verifier. So you need it to be, it's supposed to be called that. Now, last time when we tried to do this, cut, we discovered at the end that something had disappeared. I don't remember what it was. It became the process. So today I'll not be doing it. Now, let me again remind you something I've mentioned maybe again. Let me just repeat it. Okay, using the ultra honk. Using the ultra honk, there are two ways, there are two steps. The first step is to generate solidity verifier, and the next step is to generate solidity verifier.sol. So, and I said maybe you can use, for me, I normally do move the whole thing to this, or you can just rename it. I've never tried renaming it, but I still think it will still work. Now, but now, if we are doing it using the other method, using the KEKAK, you just do BB, write solidity verifier, and then target VK or target. This is supposed to be verifier.sol, supposed to be .sol. Supposed to be so what this one does is that it writes directly to .sol. Unlike the other one, it just wrote solidity verifier. And this solidity verifier, you had again to move it to solidity verifier.sol. But this one does all those steps at once. So this is the one I'm going to use to write solidity verifier, with which we will then be deploying. That is what you just copy, and if you're going using is it called remix.ethereum.org. If that is what you're using, just go there and say compile, and then there's a place you say deploy, and it works very well. So this is the one I'm going to use. And just again, go to where it is. Let me just paste the code, the command here so that you see it, because it was not complete in my notes. So just BP write solidity verifier and target VK or dot target verify.sol. So you write it .sol, it goes to .sol straight away. And .sol is what we want. So let's just do that. So you'll see that that file created. So it is okay, it's done. So it says solidity verifier saved to target verifier.sol target. So when you come to target, inside there, you're supposed to see verifier.sol, and it's here. You can see here it is. This is the solidity verifier. So it begins by SPDX, license, identifier. This is the license. This is the license, and then copyright that, programmer solidity, and so on. So this is therefore the contract. So if you want to deploy it, you just copy this. You can just say Control A and then copy. Then you go straight to, is it called remix dot? Yeah, it's called remix. Nelly, is it called remix?
Yeah, it's remix.ethereum.org.
It's .org. So when you paste, when you go there, under that, what is there? Under that, you have we have the when you go there, we have the contract. Then you can create new. Let me just let me see what it is. Let me just see. Let's just go there. Let's just go there. You have some few minutes. Okay, let me just share. Okay, it's supposed to be, it is a remix. Okay, I'm just waiting for it to open. I didn't write the correct thing. Supposed to be remix dot Ethereum dot org. Okay, so it's now opening. So let me just share it. Let's share that. Okay, I had not planned to do this. I had not planned to do the remix one. I had planned to do the one I was just doing from my desktop. But that one is long, it's a bit longer because of time. This one is shorter. So you can see it's opening, is it? Can you see that?
Yeah.
The remix ID.
Yes, it's opening.
I think I have some, is it my, I think my network is low. It's taking some time. Hey, it's taking too long. Okay, it's now opened. Now, so let me just copy our verify.sol. I think I'd copy it, but let me again copy it so that and still, okay. Yeah, so this is how it looks like. This is how it looks like. So you have, for me, that mine I've signed in as with my GitHub, but it is not is not a must. It's not a must. So if you can see what is here. What I'm interested in is this contract. This is a contract. So if I click there, you can see under it we have some artifacts. But I want to create our contracts. So I would right click on it, new file. Then I want to name it. Verifier.sol. Now, the one you're seeing above is the one I had done earlier. This one is NOIR verified.sol. I had done it earlier, so that is why it's still here. Even the artifacts that I've just seen, I had done them earlier, so that is why you can see it's never there. It's never there. This one I created another day. Oh, I was admitting somebody and then before pressing enter. So let me just again right click on this contract and say new, and then verifier.sol. That is what you want, and then press enter. Gives us somewhere to input, so we can now paste our contract there. Now, so we have compile. We have here this one is Solidity compiler, or you can even use this one. But let's click on this Solidity. You can see we have deploy and run transactions. We have JIT. This one is okay. Mine is already connected, but it's not a must. Let's do the Solidity compiler. When you click on it, you come here. There is a compile verifier. And then just above it, we have advanced configuration. Advanced configuration, we have optimization here. But just before this optimization, let's try to compile, because I know this is a very long thing. Because of this optimization, it may compile with errors. So if it does with errors telling us that it's too long, we'll come back here and adjust this optimization. Let's just press compile. Now, so you can see it has some warning. So when you look at this, I don't know whether this color is purple or which color is this, or is it orange? There's some warning. So that means when I scroll down, when I just scroll down, I'll see the warning here. It says contract code size is this bytes, and it exceeds what is required. So that's why I said you can come here. You can come at this point and adjust. Click on this, and just let's take this one to 2000, and again try to compile. Okay, so it has already compiled. This time there's no warning. When you check here, under this Solidity compiler, there is no warning this time. There's no warning. Okay, let's we did 1,000, 2,000. Let's try one. Let's try one and compile. Now, one of them produces the gas. I don't know what gas, gas, those things, gas or what and what. I don't know what gas is. I want to find out what gas is later on. But you can see it has also compiled without warning. When we did one, it compiled without warning. When we did 2000, but when we said 200, it had 200 is the default. It had some warning. Now, once it compiles, the next thing you need to do is to deploy. And at this point, we have deploy and run. Deploy and run, that means when you click on it, now it has already taken the environment, has already been given to you. It's okay. Remix is able to detect the best environment for your for your contract. So you don't need to adjust this. You don't need to. Of course, you can select, but once you paste there, it's able to tell best environment for this contract. But if you want, you can choose the other environment. You can say injected provider, MetaMask, we have Remix, that, we have Remix, this and that. And these environments keep on changing again. From time to time, you can find one is there, it becomes obsolete, then another one, other environments come with the time. There is this account, there's that. Okay, estimated gas. This is the gas I was talking about. So when you do one and do the other one, there's one that reduces the gas, another one increases the gas. Now, but okay, the contract is this. The contract is this. Now, if you check here, you cannot see what we wrote. What we wrote was a verifier.sol. But check our contract. This is our contract. This is what we pasted. This is what we pasted. And what we pasted at the bottom of it, there's a contract. At the bottom of it, it says contract Hong verifier is base Hong verifier. So you can see this is already detected for you base Hong verifier. This is what the contract, when we did solidity verifier, this one came automatically. So the contract was written for us. So you need to have this command. It does for you, it comes for you. The only thing that is missing is a code that we need to write that now encloses this contract. We need to write a code that encloses this contract. Now, okay, let's try to deploy this and see what happens. It says this contract may be abstract. It may not implement, or it may not implement an abstract parents. So that means there's a code that we need to write, and that code now, what it does is it encloses this. So that code picks some of the commands here. Pick some of the commands. I don't know, I had written. There's one I had written in the morning, but maybe because of time when we meet next, we can try and write the code that now encloses this so that you can now deploy. But as it is, when you try to deploy it, it says it's abstract and therefore it cannot be deployed. But it's this is the contract. So you just need to write that. You need just to change a few things here. Okay, you write a code, and that code is the one that now encloses this. It's called an encloser. Is it called? I think it's called encloser. So it will take this contract and a few functions. So there are so many functions here. So you don't take all of them, just a few of them. And when we meet in our next class, maybe that one I'll now be showing you some functions here. So we pick a few of these functions and put in our new code, and then enclose this, and then deploy. Now, if we are doing it from our CPU, the other format, it will be slightly different, but a bit longer. But this one is faster. Only that after this, you need to write some code that will then enclose this. Okay, that is what I wanted us to cover today. So maybe when we meet next, and of course, you can also try at your own time, find out how do you write an encloser, a code that will be enclosing one that you see we generated using BP. We generated a proof using BP. So that means the contract generated is longer, and apart from longer, has a lot of a lot of functions, and so it must be enclosed. Unless somebody has a question. Unless somebody has a question, I leave you at that so that you also go and research. When we meet next, we can discuss how do we write code that would then enclose this solidity verifier .sol so that we can deploy it on Remix. Otherwise, if you're not doing it with the Remix, you don't require the code to enclose. You don't require that code that encloses.
Mwalimu, where can we
Yes.
find?
Pardon, I can't hear.
Where can we find the notes for today's session?
Yeah, I sent them to Alex just after this lesson.
Okay,
Then,
okay.
yes.
Thank you.
Okay, welcome. Okay, another question? If there's no question, then we can stop at that so that we meet in our next lesson.